Okay, let's dive into these network scale assessments, and we'll start off reminding ourselves of the sort of spatial scale that we are dealing with here, with not at the site scale, but the site scale is a scale at which we have an extent of the reach, resolution, say of individual habitat units or individual cells, 10 centimeter, 1 meter, what have you. Those produce maps of habitat quality and or capacity. They might be summarized like this and sort of summed up into summary metrics. We might be able to do that on a whole bunch of sites on a network, but what we're interested in for supporting lifecycle modeling is getting these on a network scale summary. Why? Well, the reasons are that this scale is the scale at which we manage individual reaches, right? And so we need to strategically identify and prioritize where we can direct our actions. We need to resolve the why, not just the what that might come in some sort of watershed blob map of the overall condition. But, if this isn't in the green, if this is in the red, why is it in the red? Where specifically? And what could be done to make improvements there? So, our entry point, if you recall from last week into river styles, was the valley setting. And the valley setting we described by first having our valleys mapped as valley bottoms. And very quickly, our valley setting, we broke into confinement. So that's what our first two tools are going to be about here. So the valley bottom is a delineation that we can do, and we define the valley bottom. I don't have the definition listed here on the slide, but it is the space that could plausibly flood in the contemporary flow regime. And being that space, it's really important to understand, what's potentially in play, what could flood in better conditions, and what's the maximum probable extent of riparian vegetation. This is basically both a lens for opportunity with riparian vegetation, habitat, and flooding being opportunities, and also risk where that flooding may be in conflict with existing land uses or critical infrastructure. And so we have a tool that we developed here at Utah State. Jordan Gilbert, who is now a PhD student up at University of Montana, and he developed the first version of this, and it is based off of one of Hervé Piguet's tools, which and his group developed, called the Fluvial Corridor Toolbox. It's a really simple algorithm in the Fluvial Corridor Toolbox for trying to extract valley bottoms. Basically, you feed it two inputs. Those are a digital elevation model and a drainage network. Okay. Once you have those, then you basically look for, within a buffer from the stream, you look for flat areas. Now, the problem with the Fluvial Corridor Toolbox algorithm was you have a knob, and that is what's flat. And so you could do a slope analysis of the DEM and say, right, anything below, 2%. But what's flat kind of varies where you are in the network. As you get into steeper headwaters, then oftentimes what's flat is a little steeper than what's flat down in the bigger main stems. And so the buffer that we looked in, as well as the slope analysis that we used, so less than 5 degrees down here, less than 7 degrees here, less than 12 degrees up here, varied. And what that does is it gives you a space within which you can look at this as being a potential valley bottom. This is not a hydraulic definition because our definition of valley bottom is the area that could plausibly flood in the contemporary flow regime. It is not, for example, the 100-year floodplain or 500-year floodplain, which have in this country legal ramifications and are usually arrived at from running hydraulic models. You're not going to run, and a very accurate anyway, hydraulic model across an entire drainage network. So what we learned from building this tool is that we could reasonably map valley bottoms at very broad scales. In fact, I'm going to jump ahead to the next slide. And we could do this for the entire U.S. This is an example here for the entire state of Utah, zoomed in a particular basin here, the Escalante, just showing where some of these valley bottoms are. And we're doing that for the whole U.S. based off of 10-meter resolution DEMs from the National Elevation Data Set. This is basically based on the topography you see in your 7.5-minute quads. Now, everybody gets obsessed with LiDAR and the pretty pictures that they create. And indeed, this one looks a little blurry, and this one looks a little prettier and more resolved, right? But let's just look at the outputs. In red here is the output from the 10-meter DEM, and in green from the 1-meter LiDAR. Down here, it's the opposite. Green from the LiDAR hillshade you see behind, and red from the 10-meter DEM. Yeah, there's a few places where it's a little off, but I mean, given that this is something you can run nationally with virtually no supervision, I'm pretty happy with that sort of discrepancy. Okay, so that basically maps out our valley bottoms. And the next thing that we want to look at is confinement. Because if you recall the river styles trees, our entry point is valley setting. You need to know what your valley is or your valley bottom. And then we differentiate valley settings on a continuum of confinement.